about the differences between gas, liquids, and solids. So gas particles are super far apart. They're moving randomly throughout and very quickly, right? Liquids, they're closer together and can move freely, while solid particles are close together and held tightly in a rigid place, not moving. You can see there in the images that you've probably seen before to actually display these concepts. The gas adopts the shape of the container that it's put into, just like a liquid would, but it's harder to observe because usually gases are clear. And then, as we know, solids have the fixed shape. The only difference here between gases and liquids is the liquid has a fixed volume while a gas will expand or be confined depending on the volume it's presented. So how are they different from liquids and solids? We have the fact that they're significantly affected by temperature and pressure. Liquids are as well, but it's not as much of a change. So when the pressure increases in the system for a gas, our volume decreases. And then when the pressure decreases, our volume increases. And then it's kind of the opposite with temperature. When temperature increases, gas increases. So kind of like if you've ever seen a balloon on a hot day, if it gets colder, the balloon will shrink. Gases flow freely, so they're easily transported and mixed readily, which is great. But in a lab, gas leaks are really awful because, again, they flow freely and they're usually invisible. So it's really hard to detect them, especially if they're dangerous. So a big problem is monoxide, carbon monoxide. It's a deadly killer, essentially, because it can leak really easily and flow really freely. And they actually put in the scent that helps the detectors find them. And natural gas, usually they add scents so that you can detect them, detect a leak, because most of these gases that are kind of dangerous are usually odorless. They have low density, and that's why it's better to express them in grams per liter instead of grams per milliliter. And then our gases form solutions in any proportion. So air is a solution of over 18 gases. So we're not worried about the solubility of one gas into another. They just mix, which is nice when you're actually trying to make things happen. Okay, so when we're referring to pressure, we're going a little bit away from gases because pressure can be about a lot of things. So overall pressure is a force exerted per unit of surface area. So when you push on something, it can be used with water, with air. When we talk about gases, it's atmospheric pressure in general. We have other pressures related to gases, but mostly what we're going to be using is atmospheric pressure. So that's a uniform force exerted by all of the gases in the atmosphere on all of the surfaces below it. So the average mass of the atmosphere is 5 times 10 to the 18th kilograms, which is 5 quintillion kilograms. It's a lot. Kind of hard to envision. And again, where we live, we're used to that atmospheric pressure. So one way I like to envision atmospheric pressure is it's really similar to water pressure. I'm a scuba diver, so you can easily envision this as well. The lower you get in a water column, so the deeper you dive, it's like the weight of the water will press down more on you because you have more water above you. So think of it as each time you swim down a meter, you have one more bucket of water on top of your head. All of that water has a mass, and that's going to be pushing down against you. Same thing with atmospheric pressure. The air above you is pushing down on you with its collected mass, but the thing is, air is less dense, so we don't notice it as much as we would notice the water pressure change. Plus, it's what we're accustomed to, so it's our normal. Atmospheric pressure does decrease with increasing altitude, so when we're at sea level, we have 1 atmosphere. And then when we're at 3,000 feet above the sea level, we have 0.3 atmospheres. And this makes sense because we're getting higher, so there's less air above us than it would have been before we had done our hike. One thing to note as well is when you're doing your calculation for this lab, you don't want to use 1 atmosphere because it's not the true barometric pressure or atmospheric pressure of the room. And we'll get to that in a little bit more detail in a second. So this slide isn't necessarily important for today's lab. It is just helpful to know that these exist. There are different units of pressure, and so all of these units are represented as the atmospheric pressure at sea level at 0 degrees Celsius. So you can see the highlighted atmospheric pressure is 1 atmosphere, and then all the different types, you have pascals, millimeters of mercury, torr, pounds per square inch, and bar. Some of these might look familiar to you, like blood pressure is taken with millimeters of mercury, and PSI is for our tires. Bar is used more in the metric system from what I know, and in science we use torr a lot, as well as pascals in like physics and stuff. So it's really good to know that you can have these available to you for your conversion factors, and these are going to be given on the exam. Ideal gases, like I was mentioning earlier, they exhibit linear relationships between the volume, the amount, so they're moles, and the pressure, as well as the temperature. So those relationships I was talking about a little bit earlier. Ideal gases don't truly exist, but we can treat gases as ideal to make our calculations simpler. It basically includes the noble gases, N2, O2, and H2. They all behave nearly ideal. So this makes our calculations much, much easier. So in chemistry, you're going to expect to treat all gases as ideal for calculation purposes. And again, the temperature and volume have a direct linear relationship, so that is a positive linear relationship. As temperature increases, volume does as well. Whereas with pressure, it's an inverse relationship, indirect linear relationship, where as pressure increases, volume is going to decrease, which makes sense because kind of if you envision something squeezing on gas, and again, it's going to take whatever volume or space you give it, you're compressing all of the particles together. You're not giving them room. So now that we're talking about ideal gases, we're going to go into the ideal gas law, a wonderful, very useful, and versatile equation. So what you want to do, as the slide says, is train your brain to think PV equals nRT when you see a gas. In addition to just knowing that formula and how to use it and manipulate it, you also want to know the units that go with this relationship, because it is really important to have the same units. And I'll explain why that's really important in just a second. So P stands for pressure, and that's going to be set in atmospheres like we talked about. So if you're given something in torr or pascals, you want to make sure you convert to atmospheres before plugging into this equation. And that's going to go for any of these. Volume is in liters, amount is in mole, temperature is in Kelvin, and then R. R, we don't really know. We've never had to plug that in before. That is an ideal gas constant. So you're always going to have this. It's never going to be the unknown. And the reason these units are really important is because of our ideal gas constant. If you don't plug in atmospheres, liters, moles, and Kelvin, those won't cancel out with the constant, and you're not going to get the correct value for your math. So make sure you memorize that number. It should be provided in certain places, but I just always kept it in my mind as something to know, and make sure you're confident with the units of it as well. So there are variations of R that include different units, but we're going to stick to this, so be really careful if you ever have to Google search it. So I was talking earlier about wanting to use 1 atmosphere in experiments. There is something called standard temperature and pressure, and that describes the standard conditions for an experiment. It makes when you're reading someone else's study and trying to figure out if you've done something similar or you want to set up your own experiment like that, if they've used standard pressure temperature, you know that you're good to go and how to set it up. So these standard conditions are the temperature is set to 0 degrees Celsius, and then the pressure is 1 atmosphere. So if a question ever reads, these things were done at STP, you already know 2 things. You know the temperature, and you know the pressure. They're considered constants, and therefore sig figs won't apply to these numbers, so make sure you keep track of that in your math, but also make sure you find the note later, because we aren't actually at standard temperature and pressure in our labs here. We're not that fancy, unfortunately. So we have to record the temperature of the system and the pressure of the room, which you'll see done in the experimental part of the video later. So determining the molar volume of a gas is really helpful for stoichiometry purposes, gas ratios, things like that, and all it requires is the reorganization of our really helpful, wonderful ideal gas law. So in order to manipulate this equation, you have to know what molar volume is, and molar volume is V over N. So it's the volume of the gas over the number of moles of the gas that you have. And when you solve that, which I'll show you a little bit later how to actually go through and manipulate the equation for it, it's going to be expressed in liters per mole, which is a really important thing for your mathematics, just general concepts. Make sure you don't get it confused with what we know our concentrations to be, so molarity. Molarity is expressed in moles per liter. This is flip-flopped, so we have liters per mole for gases, moles per liter for our solutions. Make sure you don't get those confused. We have our most common molar volume that is used is the standard molar volume, which makes sense with the name. And the way it's found is using our constant, so R, and then our temperature and pressure at standard temperature pressure conditions with the right units. Makes sense. So the standard molar volume is going to be the volume of 1 mole of gas, of an ideal gas, at standard temperature pressure, and it's going to be about 22.4 liters. This is a number, again, you're going to want to know for your own material, for your tests and things in lecture, but not necessarily for this lab. You're going to be determining your own theoretical molar volume for this lab. So just acknowledge this and then make sure that you are doing your calculations differently, okay? For the actual experiment, students, i.e. the person demonstrating the experiment for you, is going to determine the molar volume of carbon dioxide under real-time conditions. Keyword, key phrase. It's not standard, so we do not have standard temperature or pressure, so you're going to be using the things given in the actual lab video, and then we are generating this carbon dioxide using a reaction between calcium carbonate and an excess amount of hydrochloric acid. So this is our equation that we have. It's balanced, so we're showing you just what's going on. And then essentially we're using what's called a generator, but it's really a water bath. We have graduated cylinder, test step, setup, and everything, and we're going to show you overall what's happening. But we're recording the mass of the calcium we've used. We don't really care about how much hydrochloric acid we used because, again, that's in excess, but it's important to limit the amount of calcium carbonate we've used because, again, if we add too much, we're going to make too much gas that the glassware can handle, and if we have too much volume for our gas, things don't go well. You've seen like when a soda gets shaken up. Not a good time. So we're going to record the volume, the environmental conditions as we talked about before, and determine the molar volume of the carbon dioxide. Then we're going to use the ideal gas law to determine the theoretical values. So you're going to be finding the molar volume measured or actual in your experiment, as well as what theoretically should have been. And then you're going to do a percent yield, as well as a percent error. So this is going to be our lab setup. We've prepped a few things for you. So we have our 100 milliliter graduated cylinder. That's going to be where we're collecting and reading the volume of gas that we create. We have a thermometer so we can determine the temperature of the system, which we'll use in our calculations later. And we have a flooded tube here. We want to make sure we flood it with water first so there's no gas that's unaccounted for when we create the gas later. Before I get started, I just want you guys to know you don't have to record any data during this segment. I'm going to throw out some numbers, but we're going to have a data table at the end of the video as well as just on Blackboard for you to do your math later. So we have our 10 milliliters of 2 molar hydrochloric acid here. It is in excess for our experiment just to make sure that the gas is created to completion. And then we have about 0.36 grams of calcium carbonate here. We're going to use 2 test tubes here, different sizes. That way we can control when the two substances interact. So I'm going to put the calcium carbonate in our larger test tube. The instructions say to do it differently how I'm going to do it, but we find it's a little bit easier to do it this way. And then I'm going to get my hydrochloric acid in our small test tube here. And I don't need all 10 milliliters, like I said, we just have it in excess so that we know that it will react with every amount. So I'm going to slide this gently down so that it doesn't splash out and start reacting. We don't want to have the reaction yet because if gas is formed, it's going to go into the atmosphere and we can't measure it. So what I'm going to do is carefully remove the top of this tube here. I've capped it with my thumb and I'm going to try to quickly attach the tube at an angle so the least amount of air gets into the system. So we have a small air bubble here. That's okay, but what we want to note that that's happening in trial 1 for our error when we calculate that later, because that is gas that we have not created, but it will be accounted for in the volume. So you see the calcium carbonate down here, our acid is in here, and we see that there's no air in this graduated cylinder. What I'm going to start to do is tilt, and we will immediately see a reaction created. So look for the clues, what we've talked about previously, about when you can tell a reaction is occurring. So in this case, we see the creation of a gas, so we're seeing bubbling pretty much everywhere. If you look down at our CaCO3, you can see the bubbles created here, and you can also see the gas being produced here. So I'm just going to keep tilting this back and forth until all of the calcium carbonate is gone. If we do not dissolve all of the calcium carbonate, our calculations are going to have error. So we want to make sure everything reacts. And essentially, if you can't see that the calcium carbonate is not dissolved, you can know that the reaction is done when the bubbles have stopped. So we still have a little bit. All right, but now if you look, our solution is relatively clear and colorless. The bubbles have stopped being produced and it's pretty much out of our system here. So now what we can do is record our final volume of our gas here. So we have, this is just like reading the volume of a normal system or a normal graduated cylinder. It's just upside down. So we have approximately, we want to make sure the lines are lined up and that it's even and level with the ground. We're going to have about 71.9 milliliters of CO2. And then our temperature of the system is 22.9 degrees Celsius. All right, so now we're gonna move on to the calculation section of the lab. I'm gonna run through a trial that we are not using real data from, so when you're following along, don't copy this down exactly, or if you are, just make sure that you're using the real data we give you later when you're turning in your lab notebook. So we are gonna start, the whole goal of this lab was to determine the molar volume of our gas, correct? So we're gonna start with our gas law, right? Our gas law equation is PV equals nRT. Now, if you watched the beginning of the video, or if you don't know, you should be already aware of the units of these and what they mean. I'll touch on it a little bit, but there's gonna be a lot of conversions throughout this, so just make sure you're keeping track. And molar volume itself is described as the volume of the gas over the moles of the gas, and the units are liters per mole. So we're gonna make sure we have to follow that so we have a good base to compare at the end. The first thing we're gonna do is find the measured volume, the measured molar volume that we calculated, and I'm gonna do one trial, you're gonna calculate it 3 times and take the average for your comparison. So make sure you don't miss that part. I'm just showing you how to do it 1 time. You're gonna do it 3 times. So in a perfect world, we have measured out 0.36 0.00 grams of our CaCO3. Note that grams is a mass. It is not equivalent to the number of moles we have, right? So we have to first convert. The molar mass of calcium carbonate is 100.1 grams per 1 mole. This will cancel out and it'll get us to our moles. So that's going to equal 0.003596 moles of calcium carbonate. The only other thing we need to find the molar volume is our volume, right? So in this experiment, theoretically, we've created 72 milliliters of our gas. As you can see, milliliters is not equivalent to the volume that we need, so we need to convert it to liters. So we're going to divide by 1,000. We are going to get 0.072, and technically, since we've measured with a 100 milliliter graduated cylinder, it's actually 72.0. So note that we have the 3 significant figures here for a later calculation. So we're going to bring this out to 3 significant figures here. Now we can divide our volume by our N here for our trial. So we're going to take 0.0720 liters of CO2 over the number of moles of calcium carbonate we used. And we are going to get 20.02 liters per mole. Since we are dividing 3 significant figures by 4 significant figures, we're going to round our answer to 3 significant figures here. So 1, 2, 3. Our answer should be 20.0 liters per mole for that part. So this is going to be your molar volume for your measured calculations, the actual one that you see. You'll calculate this 3 more times with the actual data, take the average, set it aside for later comparison. All right, so now that we have our measured molar volume, we're going to calculate the theoretical molar volume that we should have gotten had everything gone perfectly in this lab. So we're solving again for V over N, so we need to manipulate our original gas law equation. So we're going to divide by N to get it over on this side. We still have P here, so we need to also divide by P, which will get us to the equation V over N equals RT over P. One thing that's really important to note is that V over N is the molar volume we're looking for. A lot of students will get confused because we have 2 unknown 2 letters here, but in reality, V over N is 1 unknown, 1 variable that we're looking for in this circumstance. So we don't have the data for a volume or the number of moles theoretically, and that makes sense because we're not plugging any in. R is our constant. Temperature we recorded in our water bath, but we have to note that it has the units Kelvin. We recorded in degrees centigrade, so we're going to have to convert. And then pressure we've recorded and calculated for you, so we'll provide that as well. So let's go ahead and convert our temperature. So the temperature in our water bath here was 29 Celsius, and technically it records out to 2 decimal places. So when we're converting to Kelvin, it's 273.15 that we add. So we're going to get 302.15 Kelvin for our temperature, and we can plug everything in as we know there. So our molar volume is equal to 0.0821 liters ATM mole per Kelvin times our 302.15 Kelvin divided by our pressure. Most pressures are going to be 1 atmosphere because that's standard pressure, but we actually looked up the pressure of the air barometrically today in the lab when we did this experiment, so it's a little bit more accurate. So if we go through and do the math, we are going to get a standard pressure of 24.86 liters per mole. So that's going to be our theoretical value there. put a T for theoretical. The last thing you need to do is take your measured volume, the averages of all those, and compare them to your theoretical value in 2 ways. Typically, as you guys have probably seen in all the experiments we've done before, we do a percent error. And if you remember, that's going to be measured minus theoretical with the absolute value bars over theoretical times 100. So we're going to take 20 liters per mole minus, or 24.86 liters per mole, divided by the 24.86 liters per mole. This will result in a negative value, so you want to really make sure you're getting those absolute value bars in. And then times 100, we're going to get a percent error of the 19.55%. Make sure when you're doing your calculations, you're using the average that you took. We, again, are only using 1 trial, so don't get confused on that. This is our percent error. The other one we're going to do is called percent yield. So we're seeing how much we made realistically versus how much we should have made. So percent yield is going to be the measured molar volume divided by the theoretical molar volume times 100. And the yield that we got for this theoretical situation is going to be 80.45. When you're analyzing this, remember percent error, we want lower, and anything we get, we do have to count for. We did note some things that could have been errors in our lab, and then for our percent yield, the higher the better. So you want to make 100% of your product. We made about 80%. So sort of great, sort of good. But that's going to be our calculation. Make sure you check the documents online, and if you have any questions, reach out to your TAs. The next slide is the data table here. So you want to make sure that you record that. This is also going to be available in a Word document, and I'm going to provide the environmental conditions as well in our, because we have the temperature as well as the pressure. Make sure you do the conversions from mass to moles and from Celsius to Kelvin. We have blacked out the trial 1, 2, 3 for theoretical volume on purpose because you only need to find that once. Again, because you don't have trials for theoretical. Make sure you take the average of your molar volumes that you've measured and compare that to your theoretical.